working now. Is it? Yes. Okay. So his question was, it is the field of measurable probabilities. Measurable probabilities means something, but it's, I don't know if you understood well that. I will explain it. In the course, you also say that if A belongs to P of omega, we cannot always compute P of A, okay? This would imply that the sigma field can be smaller than omega. This is the first phrase that you have to be really clear with that. Omega is a set, okay? So omega is something like this. This is omega. P of omega, which is the set of all possible subsets of omega, is something like this. You have this subset, but also this subset, but also this subset. Okay, you have all the possible subsets, including omega itself. Okay, that's called the power set of omega. Okay, it's the set of all the possible subsets inside of omega. So that's the power set. I can give you an example. Okay, if omega is 1, 2, 3. Okay, if omega is 1, 2, 3. What is P of omega? So P of omega is the set that contains the empty set, omega, of course, but also 1, 2, 3, 1 and 2, 1 and 3, and 2, 3. Okay, that's the power set of omega. It's the set that contains all the subsets in omega. And we said sometimes we can find some omega such that they are not, they contain some subsets that are not measurable. We cannot find the probability. Okay, so inside of this P of omega family, you can define a special, let's say I will take this one and this one too, of course omega, but I take a subset of P of omega. Okay, so a sigma field F is a subset, okay, of P of omega. So that's an important thing. It's not omega. Okay, so when Ivan asks, is this omega? No, omega is just one set. Sigma fields and P of omega are families of subsets of omega, of course. Okay, so a sigma field is something that is a set containing sets, A1, A2, etc. And it's a subset of P of omega. Okay, so it's not every possible subset in omega, it's just a restriction of them. Okay, so is it clear for you, Ivan?
Yes, thank you.
Okay. Okay, so the sigma fields are subsets of sets of omega. I know it's a lot of sets in the word, but so Adrien has a question. What's your question, Adrien? Sorry, I have an unexpected problem. I cannot stay to your class. I'm sorry. Yeah, there's no problem. If you have to go, don't worry. You can see the video later. Okay, it will be on YouTube. Now, we have another question from Audrey. What is the difference between the straight P and the curved P? The straight P is for probability, and it's a double P, okay? I use this double P. P of A is the probability of A. A is an element of F, okay? Which is the sigma field defined on omega. And the straight P, there's not really a straight P, it's always a cursive P. This is the power set, okay? Power set of omega, okay? Do you have any other question? No? Okay. Now, we are going to continue. So last time we proved well, no, we didn't prove, but we state the base sequential formula that tell us how to compute the probability of an intersection of events. So I want to compute the probability of events AI for I going from 1 to n. And this is P of A1 times P of A2 given A1 times the probability of AN given the intersection of all the precedent sets. AK for K equals 1 to N minus 1. Okay, and there's a particular case which is very simple, the case where you have 3 sets. So the probability of A intersection with B intersection with C, this is just the probability of A times the probability of A given B times the probability of B given A. And the probability of C given A intersection with B. Okay, this is a very useful formula. In the next lecture, we are going to do a TD, okay, exercise lecture, and you will prove this formula by induction. You can try right now, I mean, during your free time, to prove this using induction. How do you translate induction in French? Yeah, as Nabi says, induction is recurrence. Okay, so you can use induction to prove this formula is true. It's very, very easy. Okay, now we saw the notion of independence of events. If you remember, we say that 2 events are independent, and I will use this notation to say that A and B are independent. Okay. A and B are independent. If what? So A and B are independent if and only if the probability of A given B is just the probability of A, sorry. Okay, so the fact that knowing that B realize doesn't give me any useful information to compute the probability of A. And we also proved that this was equivalent to say that the probability of intersection is actually the product of probabilities. Okay, those three are equivalents. Now, we're going to see something that mixed the independence and the conditional probability. Okay, so this is the first new thing of today, conditional independence. Okay, this is the new notion of today, conditional independence. Please stop me if you don't understand something, okay? Just talk. It's difficult to me to see your chat and talk, so if you have a question, you just use your micro. Okay, the conditional independence. So there's a definition. Let ABC events such that the probability of C is positive. Okay. One says that A and B are conditionally independent. Conditionally independent okay. Okay, so one says that A and B are conditionally independent if what? Oops. Are conditionally independent if given C, sorry, given C, if the probability of A and B given C is just the probability of A given C times the probability of B given C. Okay, so this formula is very, very, very similar to the second definition of, well, the definition of independence. Okay, two events are independent if the probability of the intersection is the product of probabilities. But here we are given an additional information, which is given C. Okay, and you have the same formula. You have just to add given C. Okay, I want to attract your attention to something. Depending on what do you want to do later, okay, what's your professional goal, your idea of career, etc. You will need more or less some kind of knowledge, okay? I'm representing the mathematical part of the machine learning stuffs, okay? But depending on your profile, later you will need more math or less, okay? But I want to show you something. So on the internet, you can see the archive webpage. So this is a Cornell University website. And here you go to computer science, machine learning, okay? I can send to you the link. Okay, this is the link. And here you can find some research papers, okay, on machine learning. Take any one, for example, this one, okay, and you open the the paper. Let me just change the colors here. Yeah, okay. So this is a research paper. And you have the title of the paper, Online Learning with Simple Predictors and a Combinatorial Characterization on min-max in 0-1 games. You have the authors of the paper. You have here the way to cite this paper, the date, and the abstract, okay? You have an introduction in general, and then you have computations, main result. This is a mathematical paper, okay? You have proofs, you have computations. This is what a machine learning paper looks like, okay? So if you want to be able to read those papers and to understand what machine learning is, what are the different algorithms that we use, and how to create new ones, you have to understand the math behind, okay? So this year, this is your first year in this data engineering major. Well, you're learning the basic math to understand the next step, okay? So it's very, very important, of course, depending on what do you want to do, to really be able to understand the mathematical background we give you today. Okay, so here you see there are probabilities. Here is an expectation. This is a random variable, etc., etc. You have inequalities. Okay, this is a machine learning paper. Okay, you can take this one or any one of the papers they published. Bayesian neural networks for virtual flow metering. Okay, let's see what it looks like. Okay, again, you have the title, the authors, the universities, the date, and then the abstract, okay? Small summary of the paper. And then, okay, here you have flow rate measurements. You have different experiments here, some data, probabilistic flow model, okay? Those are random variables here, epsilon I, and again you have a lot of mathematics, okay? So if you really want to do, this is something that we saw recently, you know, the Bayes rules, okay? And the likelihood we are going to see this later. But I want to attract your attention to the fact that this is not a free math lecture, okay? This is very necessary for you. Okay, any question about the conditional independence?
Please, I don't see the link that you send in the. I don't
Okay.
see where's the link, please.
On the chat. I can send it again. Do you see it? It's in the chat.
The chat of basic of probability and statistics.
Yes.
I don't see it.
Try to send a message on the conversation. And you don't see it? That's strange. The others, can you see the link?
Yes, we can see the link.
Okay.
Yes.
Well, I can send it to you, Ryan, if you don't. I will send it to you by mail, okay? Okay, let's continue. So that was conditional independence, okay? It is useful if you have the those two informations, okay? Let's say you have this information and this information. This allows you to compute this probability, okay? Again, we will do a TD with examples next time, but I have to continue a little bit more, okay? Yeah, okay. I think that was all. Now we are going to start talking about random variables and especially discrete random variables, okay? Discrete random variables. A random variable is the generalization of random numbers, okay? And when you ask for random numbers on a computer, they are actually not completely random. They are said to be pseudo-random, okay? That's another thing you have to be aware with, is the fact that sometimes you have theoretical objects like random variables, functions, real numbers, and that's a theoretical thing. Then you have a computer thing level. For example, if you ask Python to give you a random number, it is not exactly a random number, it's a pseudo-random number, okay? And if you consider a real number in Python, it's actually a float number, okay? In French, float number is virgule flottante, okay? It's a number which has a precision. It's not infinite precision as you can have in mathematics. So it's a main difference you have to be aware with, because it can have an impact on the computations you are doing. So you have a theoretical level, you have a computer level, and you have a realistic level. And generally, you will be interested in solving real world problems. And you have to translate them in a theoretical framework. It will be generally a mathematical framework, and then try to use algorithms and computers to solve the problem. And you have to be aware about the difference of those three worlds, because you're trying to mix them, okay? So this is a main example. So random numbers are a theoretical thing. A generalization is random variables. And in the computer, we use them in a way which is not completely random. It's called pseudo-random, okay? And we will use those to represent quantities in the real world for a practical reason, and we have some uncertainty. Okay, so we use randomness. Okay, I hope it was clear. So discrete random variables. Discrete random variables are functions. Okay, so I can give you a definition here. Definition. Let E be a countable set. A function x that goes from omega to E such that for any x, okay, for any x in E, the set of omega such that x of omega is equals to x, this is on the sigma field F. Okay, so a function x that satisfies this condition is called a discrete random variable. A discrete random variable. Okay,
Sorry, function. What? It's called a discrete.
Random variable.
A function is called. Okay.
A function x that goes from omega to e, such that for any x in e, this set is in F, is called a discrete random variable. Okay. The important information here is this one. And I want to be sure that you all understand what does it means, this yellow part. Okay. It's the set of elementary events that makes capital X take the value little x. Okay. Let me give you an example with something which is not completely random, but just a function. Example. If x is the function that goes from r to r, that to x give me x squared, can you please someone tell me what's the set of omega such that x of omega is equal to 4? What is this guy? Yes, as Alban said, is the set -2, 2. Okay. Is it clear for everyone? Someone has a question? Okay. This set is called the inverse image of a particular value. Okay. So this set here, we can use another notation for the same thing, is x minus 1 of 4. Of the value 4. Okay. In French, it's the préimage. Okay. C'est la préimage de la valeur 4. Ça me donne un ensemble. Ici, -2 et 2. Okay, so it's the inverse image of the value 4 that gives you two possible solutions, -2 and 2. If this set is in the sigma field, okay, for any possible value in E, then I will say that it is a random variable, a discrete random variable. The name discrete comes from the fact that E has a countable number of elements. E is a countable set, un ensemble dénombrable in French. Okay? Ça veut dire qu'il y a un nombre fini de valeurs. Enfin, un nombre discret de valeurs, pardon. Okay, maybe we can give another example of discrete random variable. If you have a dice, this is a function from omega, or yeah, let me give this example. Omega is the set of all the people in the world, and I have a random variable x that gives me the weight of the person. Okay, so you take here little omega is this guy, and it gives me x of little omega is the weight of that person. Let's say 70 kilograms. Okay, this is a random variable. Now, what is x minus 1 of 70? Well, it's just the set of all the people that have the same weight, 70 kilograms. Okay, is it more clear?
No, I don't think it is clear.
Well, Siri doesn't think it's clear. Okay. What else? Some elementary but useful remark. Okay, remark.
Sorry, I have a question.
Yes.
I just want to be clear. So here we are saying the random variable is a set.
No, the x is a function. The inverse image of x is a set.
Okay, so the random variable is a function.
Yes, it's the function x. It's a function that takes little omega and gives me a value.
Okay, thank you.
Do you have any other questions? Feel free to ask any question. I prefer you ask me questions. I can explain it 10 times if you want, but try to don't keep any question you have, okay? Okay. I see that Alban has a question. What's your question, Alban? Because we can't find the antecedent of -4 as example, but it is not a random variable. Actually, a random variable doesn't need to be bijective, okay? They are different notions, okay? Is it okay, Alban? Mm-hmm. If you limit the definition to C, relative numbers. Yeah, don't. There's no problem, Alban. Don't worry. Try to think about it if you. But there's no problem. Okay, it's just I mean the inverse image is always defined. Okay, but it's maybe it's important to explain it. Alban says, what happens if for my x square variable, random variable, okay, x is the function that goes from R to R and it takes x to x squared. What would you say it is the inverse image of -2? Okay, so x squared is a parabola here, -2 is this. What's the inverse image of -2, Alban? No. It's the empty set. Okay? It's the empty set. Okay? So that's important to understand. Okay, let's continue. Voilà, c'est l'ensemble vide, says Ryan. Okay. What else? Definition of a probability distribution function of a random variable. If you have a random variable x, which is discrete, you can define something which is the probability distribution function. Okay, so let x be a discrete random variable. Okay, for example, the result you get by launching a DAIS. Its probability distribution function, in general, we call this PDF, probability distribution function, is the function pi, from e to 0, 1, where pi of x is the probability of x taking the value little x for any x in E. Okay? you have a random variable. You can define this function, which is the probability that this random variable takes a particular value. Okay. So this is a definition. Of course, an example is necessary to understand this. It's very simple. You have to remember that those things are very simple. It seems complicated because mathematical notation is quite difficult to understand at the beginning, but the concepts behind the notation are simple in general. They can be profound, but simple. Okay. Again, if we consider the dice, where's my pen? It's here. Okay. If we consider the dice again, you have x that goes from omega to 1, 2, 3, 4, 5, 6. Okay. The discrete set, the discrete interval 1, 2, 3, 4, 5, 6 can be denoted by this notation. Okay, square brackets, double square brackets. The probability distribution function of my random variable x, little x, is the probability that my random variable takes a number k in 1/6. Okay, you launch your dice. Sorry. What's the probability? Okay, you have just 6 possibilities. Okay, so here this is k or x. Oh la la, sorry. This must be k. Okay, k. Here you have the k axis. It can be 1, it can be 2, it can be 3, 4, 5, or 6. And here you plot the probability that x equals to k. What's the probability if I launch a dice that I'd get the number 1? What's the probability to fall in 1? 1/6, okay? As says Mr. Baylat, Mrs. Your colleague, 1/6, okay? So 1/6 is a number here, 1/6. I get this point here. What's the probability that x takes the value 2? It's also 1/6, 1/6, 1/6, 1/6, and 1/6. Here I have a uniform distribution. I have a uniform probability of getting any integer number between 1 and 6. If you play with a coin, okay, you flip a coin, okay, you can have 2 results, okay, and each result, let's say it's result number 0 and result number 1, have the same probability, which is 1/2. So if my random variable is x, that goes from omega to 0, 1, then the probability distribution function is the function defined on 0 and 1. And for x equals 0, the probability is 1/2. And also for 1/2. If the coin is not, it's a tricky coin, the probability will be different, okay? If you use a coin that have been modified by any physical reason, you can get different probabilities there. But if not, it's uniform, okay? Well, that's the definition of probability distribution function. I forgot to tell you, today we are going to finish at 4:15. because I have a conference just after, okay? So again, I'm sorry, we are not going to take the pause, but you will finish a little bit later, okay? Any question about this notion of probability distribution function? Is it clear? Probability distribution function. PDF. Okay. Okay. Oops. Where am I? Here. Yes. I was. What was the remark? I don't remember what was the remark. Yeah, it was a remark some time ago, but if x is a random variable, and f is a function, if x from omega to e is a random variable and f from e to f a function, then f of x is a random variable from omega to f. Okay. So you can construct from one random variable new random variables. Okay. An example I can give you, and I will ask Alexis to correct myself because I don't remember the formula. Can you please, Alexis, recall me what's the formula of EMC?
It's the mass divided by
height squared, no, I think.
Just,
Is it that? I don't remember. You know, the CMI is the corporal mass index.
Yes, I checked its mass over the height
yes.
squared.
Okay, perfect. Thank you. So if you have a person, this guy has a mass and a height, but it's a random variable. You know, it's different for everyone. So if I don't have a precise recording of each person, I have to consider this information as random. And I have this function, which is the function that takes x and y and give me x divided by y squared. So from those two random variables, I can construct a third random variable, which is the CMI. Okay, so that's the sense of the remark. If you have random variables and functions defined on those random variables, you can construct new random variables. This will be very, very useful when you have data that you want to analyze. Okay. Okay. I think that's all for the remark. What else? What else? Okay. Okay, now we have to talk about expectation. If you have a random variable, you want to know the mean value of the random variable. Okay, so what's the mean weight of people? What's the mean height of people? Okay, what's the average? That's called the expectation. How do you say expectation in French? In French is espérance. Okay, thank you, Audrey. Espérance, okay, of random variables. And it's the mean value, okay? C'est la valeur moyenne. It's the mean value of the random variable. So I have this small definition. let x be a discrete random variable, taking its value on E. That means that x goes from omega to E. Okay. And let g of E to R, a function, to R plus, okay, it's a positive function. Then the expected value of g of x is something defined by the following. The expectation of j of x is something denoted by double E, like this. Okay, it's like the double P of probability, but here it's an E. The expectation of g of x is defined by the sum. Okay, it's the sum for any value x in E of the probability that x takes the value x times the times g of x. Okay, that's the expectation of random variable g. Okay, and it's a sum, a discrete sum over the values of this random variable x. Normally you saw this type of formula last year if you were at EPF, and if you were somewhere else. It's also a regular thing people study on first and second year of any type of scientific courses, okay? So it should be familiar to almost you all. Now, you can write the expectation value in a different manner, but it's the same, of course. I have to copy this. Now, I have a proposition here. I have a result. Is that, okay, so proposition or property. This thing is actually, okay, this thing, but for x, okay, for x is, well, let me, okay, I will erase all these things. The property says that the expectation of a random variable x can be written as the sum of the probability that x is bigger than n for n equals 1 to infinity. Okay. Why? Well, it's very easy to prove. Okay. You take what does it means? This is okay. By definition, okay, it's by definition, the expectation of x is just 1 times the probability that x is equal to 1 plus 2 times the probability that x equals to 2 plus 3 times the probability that x equals to 3 plus etc. Okay, that's the definition we saw just now. And you can write this as following, okay? You say this is p of x equal to 1 plus p of x equals 2 plus p of x equals 2 plus 3, plus p of x equals 3 plus p of x equals 3 plus p of x equals 3, okay? Why? Because I have this 3 times, so I have to put it 3 times. Here I have number 2, so it has to appear twice, and you get the same things, okay? And look, you get the formula here in yellow, okay? Because I'm asking what's the probability that x is bigger than n, and I'm moving the value of n. So the probability that x is bigger than 1, okay, is this line. The probability that x is bigger to 2 is this line, infinite semi-line, and this third is the probability that it's bigger than 3. And you continue increasing the triangle. Here you have a triangle, okay? And you get the same result as before, okay? So this is a useful property tool. The expectation is the sum of the probability that the random variable is bigger than the value n, and you make that sum over n. Okay, any question about that? Let's check something. Yeah, any question?
Just one question for the definition before you showed before.
Yes.
Why does G has to be in R plus?
It's because why G has to be in R plus? That's a good question. Maybe it has not to. The thing is yeah. Yeah, it is because it is because I'm I forgot to say something here in the expectation. That's why it has to be positive. This definition, okay, this definition is in this way if we have a summability condition. If the summability condition, so it's the sum for x in E of the absolute value of G of x times the probability of x equals x is finite. I don't know if you remember when you were in first or second year, you saw in math something called uniform convergence and simple convergence. And for uniform convergence, you have this absolute value of things. So this condition here is an integrability condition that says that G has to be quite small, okay? Later, when we will study the continuous random variables, we will see that the expectation, maybe I can write it here, there's actually just one formula for the expectation. The expectation of a random variable x, even if it's continuous or discrete, we don't really care. It's defined as the integral of x of omega with d of the probability of omega. This is the general formula for the expectation, okay? And as you can see, it's an integral. Okay, it's an integral. And it's an integral with respect to something called the probability measure here. If this probability measure is a discrete combination of Dirac mass, discrete, I get the formula with the sum. And if it's continuous, I get a usual integral. Okay, I get this integral. But in general, it's an integral. Okay, so an integral, when you see an integral, it's actually a sum if you are integrating with respect to a discrete measure, or it's an integral, a classical integral if it's a continuous distribution. Now, why G has to be positive? Okay. It's actually not required to be always positive. The thing that I need is this condition. Okay. So there are actually two hypotheses. I can say that it has positive values, but it's not necessarily always positive. It can be negative if it satisfies this integrability condition. Okay, I can say it maybe in French if it's more clear. Là ici, effectivement, ça peut avoir des valeurs négatives, mais si c'est à valeur négative, pour que l'espérance soit définie, il faut que cette somme converge. Okay? La raison de cela, c'est parce que l'espérance est une intégrale. Okay? The reason for that is that the expectation is in general defined as an integral. So it's a mathematical technical reason, but it's important. And as you said, it's not necessary that the function G goes to positive number. It can take negative numbers, but if it takes negative numbers, then this summability condition has to be satisfied. Okay. If you have another question, just tell me. Okay. Okay. Perfect. What's the next thing? Let me check. Are we ready for do some exercises or not? Yeah, maybe I can finish with the expectation and then do the exercises before continue with the independence of random variables. Okay, so what are the basic properties of the expectation? Okay, basic properties of expectation. So again, the expectation is the average value, la valeur moyenne of a random variable. Okay. Let A be an event. Okay, it's an element of the sigma field F. The expectation of the indicator of A. Do you remember what's the indicator function of A? Is it clear for everyone? It's the function that takes value 1 if X is in A and 0 if not. Okay, and here it's a random variable. Okay, so the expectation of the random variable X, which is the indicator function of A, and again, this is a random variable because it's a function from omega to 0 and 1. Okay, I want to compute the expectation of this random variable. So the expectation of the indicator function of A is simply the probability of A. Okay. You can write the full definition of the expectation if you want to be convinced that this is the case. Okay, but this is very important because the expectation of the indicator function over a set A, okay, which is a random variable, is actually just the probability of a set. Okay, so you can compute probabilities of sets as the expectation of this function. Well, okay. It's a very basic result. Please try yourself to just write the definition of expectation and you will see that it's the probability of A. Okay. Now we have the main theorem of expectation, which is linearity. Okay, so this is a theorem. So let G1 and G2 functions from E to R bar. Do you know what's R bar? Anyone? What does it mean, this bar?
It contains the infinity.
Yes, this contains infinity. Okay, it's actually a circle. Okay, this is a circle. Well, it's okay. It's just the real line with the infinity values that are allowed. Okay, and let lambda1, lambda2 real numbers. In R, the expectation is a linear operator. That means that if you want to compute the expectation of lambda g of 1 of x plus lambda 2 g2 of x, this is equals to what? It's linear, so this has to be equals to what?
To lambda 1 EG1
Yes.
x plus lambda 2 expectation of G2x.
Yes, perfect. Okay. This is very, very simple if you remember the fact that the expectation is just an integral, okay? Because this linearity comes from the linearity of the integral. This is the integral of lambda 1 g1 of x of omega plus lambda 2 g2 of x of omega dp of omega. This is the integral over omega. And this is, of course, lambda 1 times the integral of J1 dP plus lambda 2, the integral of G2 of x dP. Okay, so the linearity of the expectation is just a result from the integral, the linearity of the integral. Okay, this is a very useful property because you can compute the expectation of a linear combination of random variables if you know the expectation of each one. Okay, so some very simple cases are if you have x a random variable, a y and y a random variable, and you want to compute the expectation of 2x minus 3y. This is a new random variable called c. This is just twice the expectation of x plus, no, sorry, minus 3 times the expectation of y. Okay, so if I already know those guys, I can easily compute the expectation of the new one. Okay. Someone has the microphone. It's Johan. Can you please just cut your microphone, Johan? Thanks. Okay, so the expectation is linear. Another property which is very important is the monotonicity of the expectation. And again, this is a very simple result from integration. It says that, okay, this is the result on monotonicity. Monotonicity of the expectation. Okay, this is a theorem. If g1 of x is smaller than g2 of x, then the expectation of g1 of x is smaller than the expectation of g2 of x. Okay, that's the monotonicity of E. If you pass from this line to this line, you just take the expectation and it preserves the inequalities. And again, this is obvious if you remember the fact that you have an integral. Okay, you have a positive function j1, which is smaller than j2, and you integrate this, then you get that the integral of j1 is smaller than the integral of j2. Okay, because the integral is the area under the curve. So if you have g1 here and g2, this area is smaller than that one. Okay, so the expectation has a monotonicity property. Any question about that? Is it clear? Okay, so the expectation is useful because it gives you the average value of a quantity, a random quantity. Okay, if you like to play games like poker or anything, you can compute the expected gain, okay, the expected payoff of your game. Okay, c'est le gain moyen. You have a random variable. You have something that it depends on parameters that you don't know what values they will take, but you can compute en moyenne, the average of your payoff. Okay, so that's the second property. The first property of the expectation was the linearity. The second property is the monotonicity. And the last one is the triangle inequality. Okay. Last property is the triangle inequality. That's a theorem. Triangle inequality. That says that if you want to compute the absolute value of the expectation of a random variable j of x, this is smaller than the expected value of the absolute value of j of x. Okay, so the important thing are those absolute values. Let me just put it on red or a more visible color, maybe yellow. Yeah, red is fine, I think. Red should be fine. Okay, they change the place where they are. And again, this is super easy to be convinced of. Take a function, okay, you take a function here. This function is j of x. Let's say is this one. This is j. What's the absolute value of j? Well, it's the symmetric here. This is the absolute value of j. What's the integral of j? Well, it's the area under the curve. This area is negative. This one is positive. So the difference is smaller than the sum of the okay. is smaller than this one. Okay. If you take the absolute value, you make everything positive, and if you compute the integral, you get something bigger than if you don't take the absolute value. Okay. So that's the third property. Okay. Any question about that? Okay. Maybe we can do some exercises. Okay. We can start using maybe I have different exercises for you. Let me find one which is interesting. Okay, maybe this one. This is a very classical one. Okay. Okay, so you have a medical test. Okay, so we have a medical test. Medical test. Okay, that gives a positive result. A positive result in 99% of the cases where the patient is infected by the disease. Okay, is infected. Okay. Now, this test, okay, has in 2% of the cases is a false positive. Okay, in 2% of the cases, okay, we have a healthy patient that has a positive test. We have a healthy person, with a positive test. Okay, so it's a false positive. Okay, and we have also statistical data that says that the prevalence of the disease, okay, is 1 out of 1,000 has the disease. Okay, in the population, 1 over 1,000 people has the disease. Okay, now your job is to compute what's the probability okay, that a patient with a positive test is actually affected by the disease. That a patient with a positive test is infected. Okay, do you understand the question? So you have tests. Let's say it's a, I don't know, a a coronavirus test. Okay, this test is 99% accuracy if the person is infected by coronavirus. Okay, so if you have coronavirus, in 99% of the cases, the test is positive. Okay. Now, in 2% of the cases where a healthy person, in 2% of the cases, we have a healthy person with a positive test. So it's a false positive. Okay. Now, if we look in the population, 1 people over 1,000 have actually the disease. Okay. Now you have to compute the probability that a patient with a positive test is infected. Is it clear for everyone? Take 10 minutes to try to find the answer. Okay. And if you find this probability, just put it in the chat. Okay. And we will discuss later. Okay.
Lisa,
Yes, do you have the result?
can you put back the exercise screen?
Yeah, sorry, I forgot I was sharing my screen. Let me just share you the window. Sorry. Thank you. Franklin, can you, sorry, Ryan, can you just cut your micro because you have a lot of noise? Thanks. Do you have any, I don't know, are you lost? Not so lost, completely lost? I also have a question. Who doesn't speak any French? So who don't understand a word of French? Okay, Melissa, okay, you don't speak any French, okay. Who else?
I think it's just me.
Okay, it's just you, okay. I ask that because I have, there's a book I really like, and I will try to read you some parts of the book. And it's a French book. So unfortunately, it's not in, I think there's not an English translation, but maybe I can, I can try to translate it myself. The book is, let me remind the name, it's Méthode probabiliste pour les phénomènes réels. So it's probabilistic methods for real phenomena. It's a book from a French mathematician called Bernard Bozamy. And this professor is, well, he's not longer a professor, he's a CEO of a company called the Société de Calcul Mathématique in Paris. And he's a very interesting mathematician and CEO. Because you have to understand something. You have essentially, I don't know, two worlds. You have the academic world and the real world, okay? In theory, you have things that works and in practice don't. And you have to understand clearly and in a fine manner when you can apply this method, when you can't. Is it the conclusion that I get from this theory reasonable? Is it true? Okay, and this is a very good book on those questions. But okay, just Melissa don't speak French. Okay. Okay, with regard of this question of the disease, is anyone okay? So Xingyu find 4.72%. Anyone else find an answer? Audrey find 97%. Okay. Okay. Okay, let me correct the exercise for you. Okay. Now, when you have a mathematical, when you have any problem, any type of problem, any type of question, you have to organize the information you have. Okay, so you say, what's the information I have? What's the question I want to answer? And what are the tools? It can be equations, it can be theories, it can be theorems, it can be different conceptual tools I have to answer the question. Okay, so here we have some information. If M is the event, well, maybe I is the event, the patient is ill, the patient is ill, okay, he's sick, plus is the event, the patient has a positive test, and minus is the event, negative test. We have the following informations. We know that the probability that the person is ill is 1/1000. That's the probability for a person to be ill from this disease. We also know the conditional probability. We have the probability that the test is positive given the person is ill. This is 99%, so 0.99. And we have the probability that the test is positive even if the person is not ill. Okay, this is the false positive information. And this value was 0.02. Okay, so this is 0.02. Okay, now what's the question? The question is, what's the probability that the person is ill given the fact that the test is positive? We want to compute the probability of I given the fact that the test is positive. And here you have to use the retrodiction-based formula. Okay, if you remember the thing, it was that the probability of A given B divided by the probability of B given A. This is the probability of A divided by the probability of B. This is a mnemotechnic way of remembering the formula. It's P, it's symmetric, but in general, we use it when you pass the denominator to the right-hand side. So the probability of A given B is the probability of A times the probability of B given A divided by the probability of B. Okay? This is the formula that will be used in this case. Now I apply that formula here. So the probability that my patient is ill, given the fact that the test is positive, okay, it's equal to the probability of getting getting a patient which is ill times the probability of having a positive test given the patient is ill divided by the probability that the test is positive. Okay, so look that here we have this information, but we want the symmetric one. Okay, and if you want the symmetric one, you have to think directly to the base formula. Okay, the retrodiction base formula. So if we use this computation, we get 0.001 times 0.99 divided by 0.02, okay? And you get something like, I don't know, I have to compute it. Let me check. Where's my calculator? Here. Yeah, so it's 0.001 times 0.99 divided by 0.02. You get 0.0495. Okay, this is 0. Oops, where's my pen? 0.0495, which is 4%. 5%. Okay, let's say it's 5%. Okay, so if this person has a positive test, it has only 5% of probability to have the disease. Okay. Any question about the solution of the exercise? Yes, so Beilat, je sais pas, I don't know how to pronounce your name. Can you use the microphone?
Yes, I don't understand why the probability of the positive test is 0.02, because it's probability for healthy person with a positive test and not a positive test.
Yeah, you are right. Yeah, right. Sorry, yeah, you're right. You're completely right. So 0, yeah, this is P of I bar, and we have to compute the, yeah, you're right. I'm sorry, I was too fast. We have to compute this guy. Okay. So how do we compute P of positive? We don't have this information. We have to compute this, the probability of this event. Here we are going to use another formula we saw last class, which is the total causes formula. Total causes formula. Okay. And the probability of being positive, okay, is equals to, you remember this thing is the following. You have different events, and you have, this is A, maybe in another color will be clear, This is A. This is B1, B2, B3, Bn. And you have to compute the probability of A. And the probability of A is the sum of the probabilities of each part. So this is the probability of B1 times the probability of A given B1 plus the probability of B2 times the probability of A given B2 plus etc. In this particular case, okay, we have our population, which is divided on ill or not ill. Okay, so I have two blocks, ill and healthy. And I want to compute the probability of a positive test. This is positive test. Okay, the white thing is positive. So the probability of having a positive test is the probability of being ill times the probability of having a positive test given ill plus the probability of not being ill times the probability of P given I bar. Okay. Now, the probability of being ill, we say that it was 1/1000 times the probability of having a positive test given the illness was 0.99 plus the probability of being not ill was so the 0.1 minus 1/1000, and the probability of having a positive test if we don't have the disease is 0.02. Okay, now what's this value? I have to compute it. So 1/1000 times 0. Yeah, you have a question?
0.02.
0.02 is because we have 2% of false positive.
No, it's this value.
Sorry?
The probability of plus the in the chat. I put it in the chat. The result of this calculation.
How many?
The 0.0209.
Thank you. Okay, so if I come back to my computation, I have to replace then this 0.2 by 0.029. You said 9, no?
There is a 0 between 2 and 9.
Okay. Well, it will not change dramatically the value. Maybe here it's a 7 or something. A 3 or something. Okay. It was not a big mistake in the final value, but it was a huge mistake of reasoning. Okay. So thank you very much, Simon, for your remark. Okay. That was an important thing. So the probability of plus is the probability of being ill given that we are, the probability of I times the probability of getting a positive test given that we are ill plus the probability of not being ill times the probability of having a positive test given that we are not ill. Okay, thank you. Is this clear for everyone? Do you have any question? about the problem, about the solution? No? Okay.
Yes, I had a question.
Yes.
I don't get it because we are talking about a test that indicates if the person is ill or not.
Mm-hmm.
And the question is, what is the probability to have a positive test if the person is ill? So it should be a higher probability than 4%, no? Or no?
No. It's actually the why this exercise is interesting, because of the intuition, our intuition, which is false, tends to suggest us that this value has to be bigger. Okay, but when we compute the real value, we see that it is not so big actually. So if I have a positive test, the probability that I am ill is slow. Sorry, the probability that I am ill, given the fact that my test is positive, is low. It's counterintuitive, okay? It seems very strange, but it's true. And as Johan says, it's because the proportion of ill person is very low. Yes, exactly, okay? So the probability of being ill is 1 over 1,000. If you increase this probability, as Johan says, you will increase this part of the equation. And if this is bigger, then this becomes bigger too. Okay. And of course, if the probability of having a positive test given I is bigger than that, but it's almost 1. So another possibility is to have a positive test here, which is smaller. If you want to increase the fraction, you can either increase this value or decrease this value. If you decrease this value, that means that the probability of having a positive test is lower, okay? Well, any other question? Is it more clear, Audrey? Try to rethink about.
Yes, thank you.
Okay. Okay. Perfect. Now, another exercise for you about independence. Sorry, let me check. I think I'm adding a page where I don't have to. Yeah, here. Okay, here is another exercise about watches. Okay, maybe I can use my keyboard instead of writing things. Yeah, so two factories, A and B, produces watches. Okay. And factory A produces on average 1 over 100 defected watches. Okay. And B produces on average 1 over 200 watches. Okay. Now you consider that a retailer receives a container of watches from one of the two factories, from one of the two factories. Okay, but factories. Okay, so it's A or B, and it's an XOR. Okay, A or B. But he does not which one it is. If he don't know if it's A or if it's B. Okay. He checked the first watch. Okay, so he checked the first watch of the container, okay, and the watch works. The watch is okay. Now the question for you is, what's the probability that the second watch is also good? And the second question is, are independent the state of the two watches? Okay. The state, okay or not okay, of the two watches are independent. This is your exercise for today, and if you don't finish it today, it's not a problem. We can correct it. We can make the correction next time. Okay. Okay, so my seminar is at 4:30, so we have 45 minutes. Okay. Okay, so Xingyu give us an answer, 99.25%. That's an answer for the first question, Xingyu?
Yes.
Okay. Is there anyone who has finished also?
I think I have, but I have no calculator, so I cannot give an answer.
Okay. Okay. Zekun also gave us an answer. Okay. It can be interesting if one of you both try to explain us your reasoning, okay, the way you find the answer. Can you please try to explain what?
I have a question.
Yeah.
What he do when he picked the first watch? Does he put it in the stock or?
Yeah, you have the stock of watches, and you just pick one of them.
Okay.
Okay.
Can I try to do what I?
You want to explain what you are doing?
Yes.
Yeah, sure, sure. If you want, you can share your screen also. If you have,
I have
share.
I have a paper. I don't.
Okay, don't worry. Okay.
So I define two events. The first event I call it A, and it is the event when the first watch is good.
Mm-hmm.
The second I call it B, and it is the event where the second is good. So I try to calculate the probability of B knowing A.
Okay.
So as we made before, it is the probability of B multiplied by the probability of A knowing B over the probability of A.
Yes.
First, I calculate the probability of A using the formula of total probabilities. So it is. I find 0.5 multiplied by 0.99 plus 0.5 multiplied by 0.98 because this value are the value where the watches are good, the probability, and as we have two kind of factory, this is why I use 0.5.
Okay. And what's the final value you
find? Finally I find 0.99.
Okay. For the moment, the person who find the correct value is Xingyu. Okay, so you are not far, but there's something missing. It's difficult to me to see what's missing in your reasoning because I don't have your paper, but I will correct, or maybe Xingyu, you want to explain maybe what did you do to find the answer?
I need to show, I need to write something. May I write something?
Yeah.
Where can I write some? I can write in the chat, I think. Let us consider 8 cases. The first watch is produced by A, and it's okay. And the second watch is produced by B, and it's okay. I will write something.
Do you have something written on your screen, or you did it in paper?
I write it on paper.
Okay. Okay. If you want, I can correct the exercise, and you will check if it's similar to the things you did. Okay, you all, because yeah, it's a little bit difficult to follow the say you say without the paper. Okay, let's correct the exercise. This exercise is interesting because sometimes you have not the complete information, and you need to introduce some hypotheses. Of course, those hypotheses have to be reasonable. Okay. Okay. So the thing I'm going to say here is to give some letters to things. That's something that you are, I think, now quite familiar to, because in math we always introduce letters. So I will say that xn, okay, is the state of the nth watch. Okay, I have a lot of watches, and xn is the state of the watch. It can be 1 if it's okay, and it's 0 if not. Okay, so xn can be 1 if okay, and 0 if not. Okay, so this is the notation I will use. Now I have another quantity. I have another information that I have to encode into a letter, which is the origin, the factory that my watch comes from. So I will denote F, the factory of origin, the factory of origin. It can be, of course, A or B, X or B. Okay, I don't know. It's maybe A or it's maybe B. Now, something that I have to introduce, this is an additional hypothesis, is the fact that I will say that it's 50-50. Okay, I have 50% of chances that the watches comes from A that from B. Okay, this is an hypothesis. 50% of chances that F is A or B. Okay, 50-50. Now, I will assume something else. Okay, I will assume that the states of successive watches are independent. Assume that the state, okay, the states of watches are independent. This is also an hypothesis. Okay, and I have to compute this this means that the probability that the first, the first watch, the first xn is x2 actually. x2 is working and x1 is not working, given that the factory is A, I will assume that this probability is the same as the fact that the first watch is 0 given A times the probability of x, sorry, this is a 1, times the probability of x2 equals 1 given A. Okay, so this is the mathematical translation of successive watches are independent. Okay, the states of successive watches are independent. This is the mathematical transcription of that hypothesis. Now we have some data from the problem. We know that the probability that the state of the nth watch is 0, given that the factory is A, okay, given that the factory is A, is 0.01. Okay, this is data from the problem. Okay, and the probability that the state of the nth watch is 0, given that the factory it comes from is B, is 0.005. Okay, this is data of the problem. I know that. Okay. Now, what do we need? We want to know if the first one is good, the second one also is good. Okay. We want to compute. I want the probability of x2 equals 1, given that x1 is 1. You take the first watch and it's working. You want to compute the probability that the second watch is also working. Okay? And this is by the base formula, the probability of x1 working and x2 working. x1 is equal to 1 and x2 is equal to 1 divided by the probability of x1 equals 1. Okay, this is just base formula. Okay, base rule. Okay, now again, as in the medical example, we have to use the total causes probability, okay, to compute the denominator. How do I compute the probability that the first watch is 1? Okay, well, I use the total causes probability. That means that the probability that x1 is equals to 1, okay, will be equal to the probability, you know, maybe I can draw something. You need to condition by the fact it comes from A or B. So you have here, what's happened? Okay, this is the potato containing all the watches. This is omega, and some of them comes from factory A, and some of them comes from factory B. Okay, and I have here another event, which is the first one works and the second one also works. Okay, so this probability, sorry, it's not the numerator, it's the denominator. Sorry, here I did a mistake. I mean, maybe this way. Yeah. Ah, perfect. I don't want that thing. I want the thing here. Okay. So this green event is x1 is 1 and x2 is 1. Okay. This probability, okay, x1 is 1 and x2 is 1. Is equals to the probability of getting a watch from A times the probability that x1 is working and x2 is working given A plus the probability of B times the probability that x1 is working, x2 is working. Sorry, this is too short. Okay, times x1 works, x2 works too, given B. Oops. Okay, back. Okay. This is the complete computation. And now I just have to replace things to get a value. Okay, so what's the probability of A? Well, it's just 1/2. Okay, this is 1/2. Probability of B is also 1/2. What's the probability that the first two are working given A? I know that from the factory A, 99% of them are working, so it's 0.99 square. 0.99 square. Hey Siri, stop the alarm. Yeah. Plus, and in B I have the probability 0.995 square. So here is times 0.995 square. Okay. And yeah, that's the numerator, and the denominator is a similar computation. Well, maybe this is too small. Have to add a new page. New page. Yeah. I'm sorry, the thing crashed. I don't know why. Okay, so I have to go because I have my seminar, but try to finish the computation. I give you half of the answer. You have to find 0. How many? Sometimes I don't even. I have to make again the computation because I wrote quite ugly. But anyway, try to write the solution, send it to me. Okay, if you want to show me what you did, feel free to send it to me. And also, I want to show you something before I leave. You need to know how to use LaTeX. Okay, so LaTeX is a programming language to write mathematics. Okay, so for example, if you have I don't know some math to write, you have to use LaTeX, and all the papers you can find here in machine learning, they are written in LaTeX. Okay, so please, if you don't know how to use LaTeX, the first thing you have to do is you go to the site overleaf.com, you create a free account, okay, and you can follow the tutorials there to learn how to use LaTeX. Okay, is there anyone here that knows how to use LaTeX or not? Who knows how to use LaTeX? No one. Okay. Yes. Yes. So Shenku some basics, know some basic LaTeX. That's good. Okay. The other ones you have to start learning. It's mandatory. Okay. All the homeworks you at least in my case, you have to give them to me using LaTeX. Okay. Okay, so see you next time. Please finish the exercise. If you want to send me your solution, you can. And next time I will give you the solution. I can write it in LaTeX for you. Okay. Any other questions before I leave? No. Okay. Well, have a nice afternoon and see you next week.
Thank you.
Thank you. See you.
Bye.
Bye.